All right, welcome everyone to today's stream for integration. So today we just want to talk about all the topics that we have for the integration exam that is coming up soon. Make sure you just go through all this content with me, have a look which ones you need help with. All right, let's start right away. So just for today's agenda, we're going to be talking about three main topics here. The first one is going to be, we're going to go through all the integration rules that you need to know for the exam. Afterwards, we're going to talk about the methods that you can use for integration, and finally, the applications. Before we even start with the integration topic, I just briefly want to talk about some effective learning strategies that you can use to prepare for the exam. This is not just specific to mathematics or statistics, but you can use this in any of the other subjects that you're learning for the exams. Now, just make sure you stay until the end, because right at the end, I will have a surprise for you. So if you haven't seen the complex number topic yet, keep that for at the end. Majority of the concepts that we are going to talk about today are going to come as a question in your exam. There might be a question that tests you on multiple of these concepts at the same time, but if we are going through all of these concepts, most of these will get in a question in the exam. Make sure you're familiar with all the context before we start with all of our past paper questions. So for now, make sure you're ready. Make sure you've got a pen, you've got a paper, you've got a calculator. For those who are watching live, feel free to post any questions that you have in the chat. I'll be reviewing the chat as I go. So for today's goal, we just want to make sure that all the fundamental knowledge, all of the concepts that you need to know are with you. You've got notes for those. You can re-watch the stream online. It will be available on my channel, so you will be able to go back if you want to revisit one of these concepts. We only have 2 hours for the whole of the integration topic, so we will be moving relatively quickly with not many examples through most of these. After today's stream, we will have another stream, 2 hours again, but there we will be going through past example questions. We're going to be looking at computational examples over and over. But to make sure that you're set up for that lesson, I want to make sure today that all of the fundamental knowledge is ready for you. Now, just a quick introduction. My name is Marcel, or Cel, and I have been a tutor for over 12 years teaching mathematics and statistics. So now it is my wish to bring you all my experience and give you free tutoring available on my channel. Next year, you will be able to see courses that I will create designed for level 1 to level 3. Even though you are going to be finished with level 3 at the end of the year when you're watching this video, maybe your siblings or some of your friends might find this helpful next year. So for our pre-topic, for effective learning strategies, let's dive right in. One of the most important parts that keeps coming up in the research is active recall. We want to be able to cover our notes up and use our memory, long-term and short-term, to try and remember the content that we have just reviewed. So if you are reviewing all of the content with me today, make sure that you go through the stream again another time and try and remember what we talked about when you see the heading. Or if you write down your own notes, make sure that you cover those up and try and memorize them over the time. Cue cards are one of the good ways to use active recall, and also spaced repetition, which I will mention in a minute. However, it might be a bit too close to the exam time to be spending time to making cue cards right now. But if you're using this video in the future to prepare for an exam, feel free to use those. Spaced repetition is another part that the research is showing over and over to be very efficient for learning. So what we want is we want to repeat the content that we're looking at over and over with a certain amount of time. This time can increase over long term, but it is important that in the beginning you start looking at your content often, maybe once, twice a day in the beginning when you're learning, and then when you want to retain the information, maybe you look at this once a week or later once a month when it becomes easier to remember. Self-talk is one of the most efficient strategies that students use during problem solving, and we highly recommend that you try and talk to yourself in your mind when you're solving questions. Ask yourself questions. How do I know what to do? What is this question asking me? Why am I doing this? This will help you make connections for later so that you can access your knowledge when you need it for the exam. All right, let's have a look at topic 1. So we're diving right in, integration rules. Let's have a look. The first rule that you need to know is going to be your power rule. This is what you're going to use for all of your standard polynomials. So anything that has x to the power of something. This might be x to the power of 2, 3, but also 0.5, or any other fraction, 5/3. We can also have negative numbers, x to the power of -2, x to the power of -3. So here we can see our rule over here. We have the integral of x to the power of n with respect to x is equal to 1/n plus 1 times x to the power of n plus 1 plus c. So you should remember this rule by increasing the power by 1 first and then dividing by the new power. Some examples are shown below. So here at the bottom we've got the integral of x cubed with respect to x. We first increase the power to 4 and then we divide by 4. Afterwards, remember to put the plus c. You will be required to have the plus c at the end. If you've got fractional powers, like here at the bottom, x to the power of half, the same rule applies. We're going to increase the power by 1.5 by 1, which will be 1.5, and divide by the new power. Now you could put this in the calculator, 1 over the square, 1 over 3/2 to see what that will be. But in this exam, you're not actually required to do any simplifications, which is why I will leave it exactly in this spot. Exponential functions is the second type of function that you will be able to integrate. Now, the exponential function, if you remember from differentiation, it is its own derivative. So if we take the integral of e to the x dx, we will get back e to the x. And remember the plus c. Now here it's important to remember that the exponential remains the same. The power, whatever we have, remains the same. Now the examples look a little bit different than our standard rule is telling us, but that is because we need to consider that when we take the derivative, we need to use the chain rule. So we need to multiply at the end by the derivative of the inside function. And every exponential function is going to have e to some power. And whatever that power is, that is your inside function. So because integration and differentiation are opposites of each other, we need to make sure that we are dividing by the derivative of the inside function if we are using this rule. So our first example is the integral of e to the 3x dx. It becomes e to the 3x by itself. We just copy exactly as it is with the same power, and then we divide by the derivative of 3x, which is 3. Don't forget your plus c. And the second example, we have a whole function, 5x squared in the power. So we're going to copy exactly the same thing, e to the 5x squared. But then we need to differentiate the inside function. So the derivative of 5x squared using the power rule is 10x. So we need to divide by 1/10. well, divide by 10x, which is multiplying by 1 over 10x. Now there's a lot of trig functions, and I highly recommend learning a few of those just for the exam. Bench learn them a few days before exam so you have an idea of what you need to do, just so you have more time. This exam will be very, very short, especially if you're sitting all 3 papers in the 3-hour period. So most of these rules that I've written down here are also on your formula sheet. Make sure that you Google where those functions are on your formula sheet and that you're comfortable using the way that they're displayed in the table. So I'm not going to go through all of them as you can see them, but the most important ones that we've got here is going to be the integral of sine x dx is the negative of the cosine plus c, and the integral of cosine is the sine, and of course the plus c. Now, we previously talked about the power rule, where we can have any power of x. There's just one power that doesn't actually work, and that is -1. Well, why does that not work? And if you actually try that in an exam, that's okay. You'll figure it out. It doesn't work. So if we have x to the power of -1, we first increase the power by 1, which is going to be 0, and then we divide by the new power. Well, the new power is 0, and hopefully everyone knows by now that dividing by 0 is not allowed. It's not defined. So we have a problem. We need a different rule for anything that has a power of -1. Negative power means we move into the denominator, so this is why we have a rule for 1 over x. The rule that we have here is we're just going to integrate 1 over x dx, which becomes the natural log of x. Now, be careful here. If we have anything else but x, but a whole function there, we will have to use a different rule, which we will cover later. The most fundamental rule of integration is that the sum of the integral is the integral of the sum. That basically just means if we have an integral of a larger function, as long as the terms are added or subtracted, we can do them one by one. So let's have a look at our first example, 5x squared plus 4x minus 1. We want to integrate this function. Well, instead of integrating the whole function, what we can do is we can split this up one by one, each term independently. The reason why we want to do that is because now we can apply those rules that we have already learned. The power rule, for example. Each one of these situations is going to have one of these power rules. Even the last one. What is the integral of -1 with respect to x? Well, that will just be x itself. If you think about it, we have an x to the power of 0, which is still a polynomial term. So we increase the power by 1, which makes it x to the power of 1, which is x. And we divide by 1, which is an easy calculation. Now, when you look at integrals in your exam, make sure that if you have a plus or minus, that you split them. This way, you will be able to do each integral one by one, and you can focus on each separately. If you happen to see that there's multiplication between these terms, you cannot apply this rule. If you have sine x multiplied by cosine x and you want to integrate this, you're not going to be able to split sine and cosine and do these one by one. This will not work. Now, another part that a lot of students usually struggle with are fractions. If we have polynomial fractions, this means we have one or two big fractions where we have polynomials at the top and the bottom. Now, there's two ways that we can work with these. One of this is going to be a separable fraction. If it's separable, that means we can split it apart. And if you have a look at our first example, 3x plus 2 divided by 2x, what we get is we have something in the numerator that is added or subtracted. So this is a way for you to identify when you want to separate your fractions. In the top, if we have a plus, that means we can split it just like we split the integral. So here we have on one part 3x and on the other part 2. Now we still have to divide each part by the denominator, which in this case is 2x. But why does this actually help us? So if we now inspect this term, 3x divided by 2x, we can cancel the x's. X divided by x is 1, leaving us with just 3 over 2. And here in the second term, the 2's cancel, leaving us with just 1 over x. Now, instead of having a fraction that we don't know how to integrate, we have separated this into exactly what we've already learned, a sum of easy integrals. We can now integrate 3 over 2 by itself and 1 over x by itself using the rules that we've just learned. Even if the fraction looks much more difficult, like the second one, we still can identify the situation by just realizing there's a plus or a minus in the numerator. So in this case, we can split x squared divided by 3x, and on the other side, minus sine x divided by 3x. Now, this question, I'm not going to encourage you to actually do this integration because we have sine x over x, but that's okay. In this case, we just want to see how the separation would work. You're not always guaranteed to have an easy integral afterwards unless you're in the exam. Because what they do is they create these questions to test you on these fundamental knowledges. So here we can see you need to separate them, and they will give you questions where it's going to work. Well, what if you can't actually separate those fractions? So in that case, the rule is we need to rearrange the fraction so that the numerator is the derivative of the denominator. So you first check, is the plus or the minus in the numerator? Can I separate them? If the answer is no, your always go-to is to check if you can make the numerator the derivative of the denominator, because this will be one of our rules that we're going to be using. Now, a trick that is going to come up in integration over and over is going to be that we split a factor from the integral outside. And we always want to make this a factor of 1. We just don't want to write 1. We want to write it as a fancy one. So 1 divided by something, multiplied by the same number. Because now the 1 over a times a cancels the a, it's technically a 1, but it looks different. So if we have a look at the example, we have 1 over 3x. We can't separate this equation. 1 is by itself. So our next go-to is to check, can the numerator somehow be the derivative of the denominator? If we take the derivative of 3x, you should know we get 3. So we want a 3 in the numerator. Then we will have the form that we want. So what we're going to do is we're going to multiply the numerator by 3 because that will give us exactly what we want. But that will change our function. So what we will do is we will then again divide by 3 to make up for it. And technically, if we write the 1/3 times 3 inside here, it will be obvious that this will be a 1. But for integration, we can move numbers that are multiplied, we can move constants out of the way in front of the integral sign. We don't need to work with numbers. So this way, we are taking care of dividing by 3 and the multiplying by 3, which keeps their function the same. But now, using that trick, we have exactly what we wanted. We have an integral where the numerator is the derivative of the denominator. Now, in this case, this is also in your formula sheet. If you forget, f prime divided by f integrated with respect to x will give you the natural log of whatever is in the denominator. So in this case, the natural log of 3x. Just remember to put the straight lines instead of brackets, because the natural log function is not defined for your negative numbers. The 1/3 that we previously had that was before the integral just happens to stay in front of whatever the integral is. So that's why we take it out, because we can easily carry it through. And of course, don't forget your plus c, and try and find the place where I forgot the plus c in this presentation. Even though I wasn't trying, I'm pretty sure I might have missed one. So don't do that in the exam. Keep thinking about the plus c. Now, in the actual exam, you're going to get harder questions where you have to separate these polynomial fractions. And here's an example that we have. So again, how do we do this question? The first part is we're going to look at, can we separate this? If we separate this, well, we have a minus in the top. That works. We're going to get x divided by 2x plus 1. And we're going to get minus 5 divided by 2x plus 1. And now we think, can we use the rule that we previously had? Can we, for both of those, make the top the derivative of the bottom? Well, if we inspect the first term, it's going to be x divided by 2x plus 1. We can no longer cross out the x like in our first example, because the plus 1 is in the denominator. So we can recognize this kind of question if we can see a plus or minus in the denominator. If you see this situation, then we need to use a little bit of a different trick. Now, we will still be using the fact that the derivative of the bottom will have to be on the top at some point. So let's have a look at our first step here. So first, we're going to multiply the numerator by 2, and we're going to divide the whole integral by 2 to cancel these out. Why do we want to do that? The reason for this is because we want to match the two x's. We want to make the same coefficient for the x's on the top and the bottom. In order to have a 2 in the top, we need to multiply by 2 to get 2x in both parts. Now, once we have this, we can expand and see what our situation is like. We're now happy that we're matching the 2x because those look like they might be able to cancel out at some point. But we still have the problem that we have the plus 1 in the denominator. Remember, this is how you recognize how to do this question and which trick you need to use in the exam. So here at the bottom, we have 2x plus 1, so we want the numerator to match that. Well, let's write in the top 2x plus 1 and see what happens. If we have 2x plus 1, then we match. But we also changed what our numerator was like before. So we have to adjust this last number to make it match. So here we have a plus 1 and a minus 11 to make a total of minus 10. And then the numerator, if you simplify this, will still be exactly the same as before. Now, what are we going to do next? Well, now we are going to use what we saw in our first example. We're going to take the 2x plus 1 that we matched with the top and the bottom, and we're going to divide those. And then the separate part, which is going to be minus 11 divided by 2x plus 1, is going to be left. And clearly these two will cancel each other out, leaving us a factor of 1 minus 11 over 2x plus 1 dx. Now this integral is still not done. We still need to do more work because we can integrate 1, but at the moment we can't integrate 11 divided by 2x plus 1. Why is that? Well, remember, we want to have the numerator to be the derivative of the denominator. In this case, if we take the derivative of the denominator, we're going to get 2, not 11. So let's have a think. How did we use our previous example to make this work? I've just copied where we were just left off. So we're left off with the integral being half the integral of 1 minus 11 over 2x plus 1. So remember, if we have a number in the numerator that we want to change, that was something that we can easily change. First, we're going to separate the integral here because we have the integral of 1 and the integral of something else that is separated by plus or minus. Just be careful, here we have a half in front of the integral, which means the half will be in front of the integral on both sides. Here, the 1 over 2 is hidden over here. So we don't actually want this 11. So we're going to divide by 11 here. We're going to divide by 11, take that 11 out the front. Not quite divide, we're going to move the multiplication of 11 out the front. Now what do we get? Now we get a factor of 1 in the numerator. Well, we wanted a number 2. So we can actually get to a number of 2, but then we have to multiply by 2, which means again we have to divide by 2 or times by half in the front. Now we have minus 11 over 4 as our number in front of the integral, but now we have exactly what we wanted, which is the numerator being the derivative of the denominator. I assume that you're comfortable integrating 1 to become x and the factor of half in front. And for this one here, we have seen a few examples now. If the derivative is in the top, function at the bottom, that just becomes the natural log of the absolute value of the denominator. And don't forget your c. Now, this was a harder example because we did multiple steps, multiple tricks in order to get there. But these are the types of questions they love asking in past papers, in the exam themselves. So make sure that you're comfortable matching these numbers, matching the coefficient, doing this trick where we separate a number to make these match. Go through this example again in your own time when you look at the live stream later on the channel yourself, just to do some practice. Here's the official rule. If the derivative is on top and the normal function, the original function at the bottom, if this is the case, we just take the natural log of the denominator and we're good. Here's another example that we want to have a look at. Now, this looks like a harder example. I shouldn't actually have said that it's a harder example. But when you look at this, the integral of e to the x divided by 2e to the x plus the square root of 2, you might look at it and be like, oh, I have no idea what to do. Well, what have we learned? First part, we check if there's a plus or minus in the numerator. Is that the case? No. So we're not going to be splitting this fraction. The second part, we recognize that there's a plus or minus, plus in this case, in the denominator. So that means we're looking for this form of derivative in the top, normal function in the bottom. Well, let's check. What is actually the derivative of the bottom? Put it aside, write it down, and take the derivative. 2e to the x becomes 2e to the x. And now the square root of 2 is just a constant that goes to 0 if we take the derivative. So the derivative of the denominator is just 2e to the x. So again, we're going to write down and we're going to have a look. We want 2e to the x in the numerator, but we're not given 2e to the x. We've done this step 3 times now, so make sure you're very familiar with this. We're going to multiply the top by 2 to make it how we want it, but then we have to divide by 2 in front of the integral sign. Now it's easy, the half stays, but the integral just becomes the natural log of 2e to the x plus 2, square root of 2. All right, next part is trig functions. Now you have already seen all the trig functions that we are going to integrate earlier on, and you've got your formula sheet on how you're going to integrate those. However, in the exam, they're not going to just give you 3 marks. They want you to do an extra step before they can actually give you the mark, especially for the higher grade questions. One of the formula sheet questions, or the pages, actually is full of trigonometric equations. There's the double angular formulas, products, there is different signs added together. There's a lot. Have a look around. Make sure you're familiar with where those formulas are, because you're guaranteed to have 1 or potentially more questions in the exam that require you to use one of those formulas to rewrite your equation in an easier form. So, just a question. Have you memorized this? What do we need to split an integral? We need a plus inside our question. So when we're looking at that question, we can separate it. Looking at this output that I've given you with the products, here we are multiplying things together. That's really loud. Oh, has my sound been off for a bit? Okay, sorry about that. So if we are mentally thinking about this question, we can have a look of reversing the chain rule because we need to divide by the chain by the derivative of the inside function. So if we're having at this look at this example here, we have the integral of 9x squared times e to the 3x cubed. Now, I want you to recognize again that we're multiplying two terms together. We cannot integrate something where we multiply terms together. So we need to have a look at something else. So let's have a look at what we can do. Integration methods. So reversing the chain rule. There's a way that we have an algorithm, a step-by-step instruction on how to do this. We call this the U substitution method. Now you should know all of the steps on how to use the U substitution method so you can use these. Often this is the case when you are looking at a question where you have multiplication of different functions, especially if they're not trig functions, because we have already seen that trig functions multiplied together, we will have to use the trigonometric identities. So let's have a look at the equation that we've got here. The integral of 4x times sine 2x squared dx. Well, we want to replace the inside function, so 2x squared in this case. We're going to replace that with a u. So now we're left with the integral of 4x sine u dx. But we can't randomly have a u there, especially not if we have a dx and an x in the equation. So how are we going to deal with these? Well, first of all, we substituted in u is equal to 2x squared. So now we can differentiate this equation, u is equal to 2x squared on both sides. Then we get du by dx is equal to 4x. We want dx, so we're going to multiply both sides by dx, and we're going to divide by whatever function we have here to get what dx is. We're going to solve this equation to be equal to dx. Now, we can replace this dx with whatever we've got, and we can see that the dx cancels out the x 4x's. So we replaced the dx with a du over 4x, and we're going to cancel these in the next step. Now we are just given an integral in terms of u with du. This is something we can easily deal with, so let's do the integral. The integral of sine becomes negative cosine. We just have a u in the brackets, so the derivative of that is 1. We're going to divide by 1. Okay, and don't forget the plus c. But well, what do you notice here? Well, first of all, the 4x cancels. If that doesn't happen in your exam, you've probably made a mistake. Because after you substitute in what your dx is and replace it with du over the function, those should cancel out. If that doesn't happen, then you've either made a mistake with your work, or U substitution is not actually the way to solve this question. But we're not quite done yet, because remember the question itself was in terms of x. So we have this in terms of u, cosine u. So we're going to have to replace it with whatever we had for u. And remember, we had u is equal to 4x squared. So once we've substituted this in, then we're done. Well, the u substitution actually takes a very long time. So what we want to do is, it's very, very easy for us to mentally check, do we have potential cancellations? So if we have a look here, if we do the derivative of the inside function, we're going to get 4x, and that is 4x here. So we're going to cancel. That's really good. And I'm seeing this is a typo. This should be 2x squared because that is what our u was. Okay, let's talk about the fundamental theorem of integration. Now, a theorem is like a rule. This is the most important rule that we use when we talk about integration. Now, you might not have been introduced using the name of it, but you should have seen how it's applied. So we're going to use this to calculate what definite integrals are using the bounds. And we can instead calculate the integral by first substituting in the upper and then the lower bound and subtracting those. So if we have an integral where we have a start point A and an end point B, what we're going to do is we're going to integrate this function and then we're going to substitute in A and B separately. So let's have a look at this computational definite integral. We have the integral from 1 to 3 of x to the power 4 dx. Well, the first thing is we're going to integrate 4x, and remember we're just going to use the power rule. So this is x to the power 5 and then divided by 5. Now our bounds are 1 and 3. So from the fundamental theorem of integrals, we can now just substitute in our upper integral, our upper bound 3, and then our lower bound 1, and make sure we take the difference. And you can just do this in the calculator. All right, we can also calculate definite integrals using numeric computations. And there's two methods that they would like you to know for the exams. One of them is the trapezium rule. When you use the trapezium rule, all you need to do is refer back to what the formula sheet says and how you're going to use it. So over here, for example, it's a very long equation, but it's just important that you remember how to use it rather than memorizing the formula. So let's have a look. First, we're going to look at the bounds. A and B are our bounds. So when we're calculating h, we need to know b and a, and those come from the integral himself. Then we're dividing this by n to get h. So n is the number of points that we have. But we need to be careful here because we're going to start counting with 0. So in this case, we're going to have y0 all the way till y5. So y5 is going to be our n. Also, we're going to notice that our y0 and yn are in our formula. So we're just going to write underneath our equation which y values we have to make sure that we can calculate these. The rest of the equation is just substituting in all of our y values that we've got. Now the Simpson rule is very similar. It's just a little bit of a longer equation, but it's done exactly the same way. So we already know where our a and b come from. The n comes from the same way. Well, y0 and yn, that's the first and the last n. So that's exactly the same as well. And then we just substitute in our values. But the Simpson rule separates even and odd terms. So just be careful when you're substituting them in that you're making sure that you're collecting the correct terms for each. All right, let's have a think about the applications that we can use during integration. Why do we actually just want to integrate? What for? One of the topics is that the area under the curve. This is one of the applications that we use. Most of the time, we're going to be looking at the area between the x-axis and the curve itself. Here's a picture, for example, of the function x squared, where we want to know the area between axis 1 and axis 3. we can use definite integrals that we've just learned how to compute in order to figure out what this area is. So if we wanted to know the area from 1 to 3 of the function x squared, we're going to figure out the integral from 1 to 3 of the function x squared with respect to x. Now, the computation of this, you should know how to do that by now. Integrate the function itself. Well, that is the power rule. Increase the power by 1, divide by 3. And then we're going to substitute in our upper bound first, then our lower bound. And we can just put that in the calculator. We will get 26/3. Now, here's another example of the area under the curve. We have f of x is equal to minus x squared from -2 to x as our bounds. Well, here we recognize that the area is truly under the x-axis, but it doesn't matter because we are just looking at the area in between the x-axis and the curve itself. So, if we do the same calculation, we're going to get the area is the integral from -2 to 2 of negative x squared. Well, if you do our computation, we increase the power by 1, divide by the new power, and we're substituting in the upper and the lower limit. We're going to end up with -16/3. It is important that the area underneath the x-axis is always negative. So in our example just now, we got a negative value for our area, but areas cannot themselves be negative. So we're going to have to make this number positive. Our calculations are correct, but the negative will just actually show us where the area is, which is underneath the x-axis. So areas above the x-axis are always positive and areas below are negative. So we need to be careful when we're calculating those definite integrals without thinking. Always sketch the function or use your graphics calculator to check what's happening. Let's have a look. The definite integral calculates the area between x-axis and the curve, but takes into account positive and negative values. So to calculate the area under a curve, we must check if the total area is under or below the x-axis. Let's just compute without thinking. What happens to this integral? The integral from 0 to 2 pi of sine of x dx. Well, we know sine integrates to negative cosine x, and then we have to substitute in the bounds 2 pi and then 0, and we take the difference. Be very careful with the negative sign here, minus and then the negative sign again. So we're going to end up with negative cosine 2 pi, which is 1, so -1. Cosine of 0 is also 1, so we're going to end up with -1 minus -1, which is 0. So the area between the curve is 0. Well, is that true? Clearly, if we draw the graph of sine x, we're going to get two separate areas. So how can this be 0? Well, one area is positive and the other one is negative because one is above and the other one is below the x-axis. So how can we deal with this? We're going to have to compute the same calculation, but not in the same way. Our computations were correct. We did exactly what we are supposed to do, and the answer 0 is in fact correct. But this does not represent the area anymore, just the indefinite integral that we've calculated. If we're ever asked to just calculate an integral, we can do this without having to think. But if the question is revolved about area, finding an area, then we need to be careful about those switches between positive and negative areas. So how do we actually find this area? Well, we can split this integral into two parts and calculate each area separately. So for example, to find the first area, we can separate the integral from 0 to pi, and then we can do an integral from pi to 2 pi. We've done some calculations already, so you can check this, and I would leave this as an exercise. So if you're watching this video on YouTube, then just pause and check later. So we know that each of those areas are going to be 2. In the second case, we're going to get -2, but we can just make that a positive number because we know areas are always positive. So we're going to get that both area 1 and area 2 are exactly 2 units squared. So if we put them together, we get 4 square units. The question is just, where do we actually split this integral? Before, I told you we're going to split it at pi, but how do we actually figure out where to split it? Because you're going to have to figure this out in your exam. Well, the answer is actually pretty easy. You just put this equation into the graphics calculator and find the x-intercept, or wherever these 2 areas change. So what about an area between 2 curves? We've already done the area underneath the curve, which is the x-axis itself, where we're comparing it with. Well, if we think about it, the x-axis itself is a function, g of x is equal to 0. So we've actually the whole time applied this rule already, just with a special case where our function is 0. So we can see that in this case, we have 2 functions, f of x and g of x, and we want to find the area between. So let's have a look. Here are 2 functions, f of x and g of x. So we have f of x is x squared and g of x is 1.5x. So how do we find the area between the curve? Well, again, we need to know where we start and where we end. So in this case, we need to know where these 2 intersect. In this case, we have an intersection at the origin and over here, possibly at about 13 or 15. If we wanted to calculate this, we can use the graphics calculator to just put both equations in and find the intersection points. Now, our rule for area between the curves is going to be, we're going to find the integral between the bounds, just like before, but we're just going to take the difference between the 2 equations. And it was actually 1.5 in the example before, not 15. So we're going to integrate from 0 to 1.5 of x squared minus 1.5x with respect to x. 1.5x was g of x, x squared was f of x, and we have the negative in the middle. We get an answer of -9/16. So why is this now negative? Well, this is negative because when we look at the picture, what we did is we took the top one minus the bottom. It doesn't actually matter what we get for the integral. We are going to be able to switch either g of x or f of x around. Just make sure that if you get a negative at the end, that this is going to be a number that you make positive. Differential equations, I think, is the last part in our application process. So we need to recognize questions that have differential equations. So what are differential equations? A differential equation is an equation that has both a derivative and a function of itself in there. So in this case, for example, we have the derivative dy by dx is equal to the original function y and something else. So how do we deal with this? First of all, we need to talk about solutions. If we want to solve this equation, what actually solves this equation? And the answer is not any x values. X is 5 does not solve this equation. Because what we're looking here is we want to find an equation y where the derivative is y itself plus something with x. So the solution for differential equations are actually functions themselves. So solutions to x squared, for example, is 1 are x values. X is 1 and x is minus 1. But solutions to a differential equation are functions. So let's have a look at an example. dy over dx is equal to 2y. We can recognize that this is a differential equation because we have a dy dx and a 2x. Now, what is this actually asking us? We can have a think. Well, we want an equation y so that if we take the derivative, it's double of y itself. Okay, can we maybe think of some equation where this could work? First of all, let's check if some of these options that I might give you are solutions to this differential equation. First of all, x is 3. Is x is 3a a solution to this differential equation? No, x is 3 is not one because we want a function y, not a point x. Okay, b, y is 3. Does that work? Well, we're going to be able to check. Y is 3. Well, if we have 2y, then we have 6. But what is dy by dx? Well, the derivative of y is going to be 0 on this side. So we're going to get 0 is equal to 6. That doesn't work. Let's have a look as y is equal to x squared. So we're going to have to take the derivative. Well, the derivative is 2x. The 2x is here, and 2x is equal to double our equation. Well, 2x is not equal to 2x squared, so that is also not a solution. Let's have a look at d. E to the 2x. If we take the derivative here, well, e to the 2x stays the same, but we multiply by the derivative of the inside function, so that's 2. So we're going to get 2e to the 2x. And on the other side, if we multiply our original function, e to the 2x by 2, we also get 2e to the 2x. So this is actually a solution to our differential equation, this function here. Now, in the exam, often you will be asked to solve these differential equations. Some might have a y, most of the time they might not. So let's have a look at one example that might come up. dy dx is equal to 3x squared. We can recognize that this is a differential equation because we have a derivative in it. So how do we actually solve this? Well, if we wanted to solve this, we need to first have just the dy. Well, here we have a dy over dx. Well, in order to get a dy, we would have to multiply by dx. So this is what we've got here. We're going to have a dy here and a 3x squared, and there should be a dx here at the end. Sorry about that. And now we have separated here everything with y and here everything with x. And now we can integrate both sides. So on the left-hand side, the integral of dy is going to be y. But on the right-hand side, if we integrate this, well, we know how to do that. Move the power up by 1, divide by the new power. So we actually get a function as our solution. Y is equal to x to the power of 3 plus c. The plus c comes because we have a family of solutions here. Lots of equations that work. You're going to be required to solve for the c. However, there's one more question I had is why is there no plus c on the left-hand side where we did the integral of dy? Well, this is because we could have a plus c on both sides. But if we move them together, c plus d or two c's together, it's just going to be some number. And we don't want to have too many of these random numbers floating around. So as long as we have one, we can always match it with the others. So here it doesn't matter as long as we have a plus c on one side. So how do we find the specific solution? We want to know what the c is. So in order to do this, we need to substitute in a value for x and y, and the question will give you information on x and y to substitute in. For example, here y is 1 when x is 0. That means we substitute in x is 0 and y is 1. And you can substitute these in as homework and see what you get. All right, as promised before, there will be surprise at the end. Yeah, let's have a look. So I will actually provide you with a worksheet where all of the fundamental concepts that we have talked about will be tested on. Now, the difficulty level might be a little bit less than an exam question, but I want to make sure that you are mastering all the fundamental concepts. Every single one of the concepts that we spoke about today, you should be able to replicate in an exam. So you'll be able to use this worksheet to go through all of these and make sure that you know how to do these. Especially the harder examples that we did in the beginning with the fractional polynomials. So our next stream, I don't know when that is going to be, but in our next stream, we're going to be doing a 2-hour stream of worked examples. Now where you have a revision of all the fundamental concepts that you need to know, make sure you remember all of those, write those down as in your notes, and be ready for our next stream when we are going to be doing 2 hours of non-stop examples using all of these fundamentals. Okay, what now? Well, make sure that you understand all of these concepts. Do the worksheet. It will be linked to the description when I upload this video later. You can check it out and contact us if you need any more one-on-one support. Thank you very much for today's stream. It's a little bit earlier than I was expecting, but the concepts themselves, there were not that many. It was mainly the application and the questions that are so difficult. If you are understanding all of today's concepts and you're struggling with past exam questions, for example, a lot of these link back to algebra. So make sure that you check out the complex number one as well, where we go through most of the fundamental algebra before we go and jump into the complex number topic. Awesome. Thank you very much, and I'll see you next time.